Cardiac output is the volume of blood pumped through the heart per minute. And that definition is something I want you to be comfortable with to wrap your mind around. Cardiac output is among the many important variables that we need to regulate if we're going to maintain homeostasis. So again, it's the volume of blood pumped through the heart in 1 minute. Cardiac output is, if you look at this equation here, it's equal to SV times HR. Now SV stands for stroke volume. The stroke volume, if you come over here and you look at our Wigger's diagram again, this is the same diagram you've seen. And we're going to look just at the volume portion right here, the volume. So remember that this is ventricular volume only. And so you'll remember that we have the filling phase here. And then right here, this is my end diastolic volume. Then we have our ejection phase, rapid ventricular ejection, and then right here we might have my end systolic volume. Stroke volume is the amount of blood moved out of the ventricle from here to here in one contraction, one lub-dub. And it's calculated by taking your end diastolic volume and your end systolic volume. And if you come over here to look at the equation, stroke volume is equal to end diastolic volume minus end systolic volume. There's another vocabulary term that you need to know, and that's this ejection fraction. Ejection fraction is often used as a marker or an indicator of cardiac performance. And the ejection fraction is calculated by taking your stroke volume divided by your end diastolic volume times your 100%. Typical ejection fractions, if I'm remembering correctly, about 60%. That seems a little low, perhaps 68%. I'll have to double check those numbers, but that's kind of a ballpark there. We never eject all of the blood that's contained within the ventricle. And so we always have a leftover end systolic volume there. This ejection fraction then would change. For example, if you were experiencing heart failure, your heart would not be able to generate the force to eject enough blood each heartbeat, and so your ejection fraction would suffer, and that would be a marker for this heart problem. Now HR stands for heart rate, and otherwise known as pulse rate. Heart rate is the number of complete cycles in 1 minute, and so heart rate calculated, not surprisingly, you're going to look at your cycle. You're going to divide it by your cycle time. So let's go back over here and look at this Wigger's diagram in terms of how to figure this out. So if I were to determine, and you can start pretty much anywhere you want, but let's say I'm going to determine that I'm going to measure from here. We'll do it an fairly easy place to mark. Let's measure from this line right here. So the moment we close those mitral valves to the next time we close those mitral valves. And if I were to look at that and measure the time on the x-axis between here and here, I might get any number of values. One average value would be 0.8 seconds. Or 800 milliseconds. So once I have that information, and by the way, in lab, you're going to do this by using the ECG. So I can use the ECG to do the same thing by measuring from R wave to whenever my next R wave is going to be. And so you can use that method to figure out what we call the cardiac cycle length. So one cycle, one lub-dub, one beat of the heart. I mean, here's your, your mitral valve. This is your lub, right? Lub. And then we have our dub and then we have our lub again. So lub, dub, back to lub. That is the whole cycle. That's one cycle of the heart, one cardiac cycle. And so going back here, one cycle divided by the cardiac cycle time, which in this case we decided was 8 seconds. And you can do the math here then. There's 60 seconds in a minute. So if I want to figure out how many cycles in 1 minute, I would just essentially crunch those numbers. I'd divide 60 seconds by 0.8 seconds. And then I would remember that the cycle is a lub-dub cycle. It's a one beat, one complete contraction. And so we could substitute the word beat for that, and that would give us beats per minute, basically. All right. These give us then, if we put them together, stroke volume, heart rate, gives us our cardiac cycle. We can do an example of that. If we were to look over here, let me give you some approximate values. Let me erase some of this mess that I've made so we can actually look at these approximate values. If I were to say that approximately speaking, I scribbled over my graph. So let's just say we're going to have 135 milliliters for my end diastolic volume. And let's just say we're going to have 65 milliliters for my end systolic volume. So now we can use that to calculate really quickly what my stroke volume is. So my stroke volume, remember, is equal to end diastolic volume minus end systolic volume. And so in this case, my stroke volume is 135 minus 65. And so that'll give me a stroke volume of 70 milliliters. By the way, I can use that to calculate my ejection fraction. If I were to take my 70 milliliters and divide it by my 135 and multiply it by 100, that actually gives me a ejection fraction of 51.9. I'm not entirely sure if that's normal. Anyway, we're going to stick with my example here. And so if I have 70 milliliters, and now let's imagine my heart rate, if we were to calculate this, we'll stick with this 0.8. So let's look at 60 divided by 0.8. That's going to give me a heart rate of 75. So we'll say this is a 75 beats per minute. So now we're going to put these together to get my cardiac output. So basically what I have is 70 milliliters times 75 beats or cycles per minute. So we're going to complete 75 cycles per minute. Okay, so 70 times 75 is equal to 500 milliliters. So that essentially means that in this particular example, this particular person, whoever we're going to pretend the person is going to be, is moving over 5 liters, greater than 5 liters per minute through the heart. And I'm hoping that that is going to strike you. You're going to look at that and you're going to think, wow, because it is a wow. I mean, this is cool. Your heart, this little tiny organ, relative to the rest of your body, your heart is moving 5 liters of blood per minute. And that, for the average 70-kilogram man, is essentially, it's your total blood volume being cycled through the heart at rest per minute. And if we were to assume that the stroke volume and ejection fraction gives us 60%, then we're actually looking at a higher volume in that case. Now, to regulate cardiac output, we're going to need to regulate stroke volume and heart rate. So we'll take a look at that in a second here.